1 functions, section 2 transformations. We're going to be looking first at this equation up here. Y equals a times bx minus h raised to n plus k. So a, b, h, and k are going to be transformations that we're looking at. B is going to come in later, so we're going to focus on A, H, and K right now. Those are the two main ones you will see. So A is going to multiply the y values, stretch and squish the graph vertically. H is going to add and subtract the x values, shift left or right based off of the opposite of the sign that you see. So if it says minus h, then you're actually going to have a positive h and you're going to go right. If it says plus h, then it's a negative h and you're going to go left. Always opposite. K adds or subtracts to the y values and shifts up or down based off of the same sign. So plus goes up and minus goes down. One thing to note here is that A has to go before K. A is multiplication to the y values. K is adding and subtracting to the y values. And order of operations tells us that multiplication comes before subtraction. The same thing is true with B and H. So moving on, we're going to look at example 1. For example 1, we're going to make a table for y equals 3x squared. So step 1, identify the parent function and the transformation. So when we do that, the parent function is y equals x squared. We know that it's x squared because when we take out the transformation of 3, that's what's left. Y equals x squared is our parent function. The transformation then tells us that it's a equals 3 because 3 is in the a spot of our original equation. It's in front of the x squared, but not inside with the parentheses. So that's a. So a equals 3. That means we're going to multiply the y values by 3. Now that that's identified, we can move on to step 2. The first thing we have to do is make a table for the parent function. To do that, we set up our table with x and y. -2, -1, 0, 1, 2 are the numbers that we're choosing for x. We do that because it gives us an idea of what's happening across the x-axis, but any numbers can be chosen. These are the ones that make the most sense in this case. After we've used these numbers in our table, we're going to have to find what y is. And we do that by looking back at our parent function, because this is the parent function table, and we fill in the x value into the parent function equation. So if y equals x squared, we change x, so -2 squared. So y is now -2 squared, which is going to equal 4. Squaring something means you multiply it by itself. So -2 times -2 equals 4. -1 squared equals 1. 0 squared equals 0. 1 squared equals 1. And 2 squared equals 4. Now that we have our parent function table, we can go make our transformation table. So if our transformation is a, and a multiplies to the y values, then that means that the x values are all going to stay the same. So we're going to copy over the same numbers into the x column, and then start changing the y values based off of what a is. So a is multiplying by 3. So we're going to take 4 times 3 and get 12. 1 times 3 and get 3. 0 times 3 and get 0. 1 times 3 and get 3. And 4 times 3 and get 12. Okay, so we have some things over here that we wanted to make sure we've paid attention to throughout what we've done. The first thing is that the y value of the parent function is found by inputting the x values into the parent function. So that's what we've done here. We take the x here that we're given, put it into the parent function, and we get the y value that goes with it. The next thing to notice is that the x values are copied over in the transformation table because only the y values are changing. So that's what we've done. We've taken the x's, we've copied them over, and then we've only changed the y values. The last thing to notice is that the input of 2 used to have an output of 4. You can see here 2 going into the equation used to give us 4, but it's 12 now in our new one because 4 times 3 equals 12. So we took the 4, we multiplied it by 3, and that's how we got our 12. You can see that it works when you take 2 and you put it into the given equation up here. Y equals 3x squared. So if I take 2 squared times 3, that gives me my answer. Of 12. Okay, moving on to example 2, we see here that we're told to graph y equals negative 3x squared. So back to step 1, the parent function is y equals x squared because when we take out the transformation, that's what we have. And that transformation is still in the a spot, so it's negative 3. A equals negative 3. That tells me that now I'm going to multiply the y values by negative 3. So with step 2, because we're graphing, we're going to graph the parent function. The parent function is the same, y equals x squared. So we're actually going to be graphing this parent function table onto our plane here. So negative 2 gives me 4. You can see negative 2 gives me 4. Negative 1, 1. 0, 0, 1, 1, and then 2, 4. So each one of these points is coming from the parent function. So I can do that on the graph without making a table if I know that I go over to 1 on the x-axis and it equals 1 because 1 squared. And if I go over to 2, I'm going to go up to 4 because 2 squared is 4. So you can just graph the table, or sorry, graph the coordinates if you know them. So then now that we have our parent function, we can look at step 3, which is to graph the transformation. To do that, we're going to take each y value that we have and multiply it by the a. So from here, right now, my coordinate is 1, 1. So my x is 1 and my y is 1. But a multiplies to the y values. So now instead of 1 giving me 1, now 1 is going to give me negative 3. And then negative 1 is going to give me negative 3 as well. From here, with 2 in the parent function gives me 4, but 4 times negative 3 gives me negative 12. So 2 used to give me 4, and now it's going to give me negative 12. And the same thing for negative 2, it went from 4 to negative 12. So now we've moved all of our points. 0 times negative 3 is still 0. So my vertex doesn't move, but all the other points move down to what they multiply to. So we have a notice here, the point has moved down from a y value of 4 to a y value of -3, because 4 times -3 equals -12. And then we have our final answer. Example 3. Make a table for y equals x minus 4 squared. So now we have a different transformation. It's no longer in the a spot. Now it's inside the parentheses being subtracted from x. So we know that this is h. So to identify the parent function, we're still working with y equals x squared because there's a squared on top of my variable. Okay, and then my transformation is h equals 4 because it's the opposite. I see minus, so I know it's positive. That tells me to add 4 to my x values. So now I'm going to go back to my parent function table that we made in the previous examples. So you can see that it's still the same. -2 gives me 4 because -2 squared is 4 from the parent function. So I'm going to fill in the rest of that and then make my transformation. So in this one, you can see that because h changes the x values, the y value is what's going to change. So you can see from the notice here, the y values are copied over in the transformation table because only the x values are changing. So this copies to here in the new table. It's going to stay the same. The x values will change by the amount h is. So we're adding 4. So -2 plus 4 gives me 2. -1 plus 4 gives me 3. 0 plus 4 gives me 4. 1 plus 4 gives me 5. And 2 plus 4 gives me 6. So I go through and I make my new table. So one thing you want to notice here, the coordinate 0, 0 became 4, 0 because we took the x value of 0 and added 4 to it. So this is my vertex. So my transformation here is going to change the vertex. It's going to move it to the right 4 spaces. So this is my final answer. This is the only transformation that's happening here. So this is the answer to example 3. Now example 4, we've got another graph to make, and this one is y equals x plus 4 squared. So instead of minus, now it's plus. So we're going to identify the parent function. It's still the same. X is being squared. And our transformation now, opposite sign. So h is -4 because I see a plus there. So I'm going to subtract 4 from all the x values, which basically is going to tell me to move each point to the left 4 spaces when I graph it. So graphing that parent function, it's the same parent function we've been working with. It's all quadratic. So 1 gives me 1, 0 gives me 0, and 2 gives me 4, and it's paralleled on the negative side as well. Now to do the transformation, I'm going to take each coordinate and move it to the left 4 spaces because h is negative. So I'm going to go backwards 4 for each one. And this creates the new graph here. So one thing you want to notice, each point moves left 4 spaces, but it stays at the same height. I'm not changing my y value. My y value would change its height. I'm only changing the x's, so it's moving to the left or to the right. So you can see that 1, 1 becomes -3, 1 because it moves left 4. There from here, 1, 2, 3, 4. So this point is actually now over here. And then we have my final answer. Example 5. Graph y equals x squared plus 5. New transformation now, same parent function, y equals x squared. But now it's outside of the parentheses and it's addition, so that means it's k. So k equals 5. what we're going to do is we're going to add 5 to the y values. So that's, for a graph, it's going to move all the y values up 5 spaces. So again, we start with the parent function. We need to know what that looks like so that then we can change it by the transformation. And from the parent function, we're going to take the vertex 1, 2, 3, 4, 5 spaces up. So each point moves up 5 spaces, but they stay above the same x value. I'm not moving left or right. I go from here straight up. From here straight up. It would be somewhere up here. There's just no room for it. So you can see how this point goes up to that point, but it stays above the same x value. So -1 becomes -1, 6. And then we have our final answer here, just with the points plotted up there that you can't see. Okay, example 6. Make a table for y equals x squared minus 5. So the k value has now changed to a minus, so we have same parent function and k equals -5. We're going to subtract 5 from the y values. Okay, so back to that same parent function table, because it's all still working with y equals x squared. We've got the -2, -1, 0, 1, 2, added a 3 just so you could see if it kept going what the graph would look like, or I'm sorry, what the table would look like. If you did try to graph these, you would get a better idea of what the graph looks like if you added that extra one. So from here, we know that the y values are what's changing, which means that the x values are going to transfer over and be the same. And the y values are what changes. We're going to subtract 5 from each one. So 4 minus 5 is how we get that -1. 1 minus 5 gives me -4. 0 minus 5 gives me -5. And then that goes with the thing we're supposed to notice. This is my vertex, and my vertex has moved down 5 spaces to now be 0, -5. Because 0 minus 5 equals -5. And you continue down the list, taking 5 away from each one, and then you'll have your final answer table. Okay, example 7. We have a different type of function now. Now we don't have an exponent on the variable at all. And the only thing that's happening, we've got addition. So we know that that means this is linear. There's no exponent or other symbol. So my parent function is y equals x. And you can see there's no, for a linear, there's no h, there's only a and k, because there's no reason to put parentheses around the x. So because I have this adding 5 on the outside, I can see that k equals 5. And if you compare that to example 8, it's the same. They're both k, but just opposite. So we have k equals 5 on this one and k equals -5 on this one. So when you have your table, the parent function table is a little different now. If I have a -2 for x, that's here. That means that y just equals that number. So x and y are going to match each other because here they match. They equal each other. So whatever I put here, the same number goes next to it. But then I do my transformation. K changes the y values, so all my x's stay the same, and I just change the y's by adding 5 here, and then same for this one, I would just subtract 5. So you can see how -2 plus 5 equals 3, and -2 minus 5 equals -7. From the two tables, I wanted to highlight that the y-intercept will change for these lines. So because you have, first it starts at 0, 0 in the parent function. When you add 5, you take that y-intercept and you move it up 5 spaces. And that's how you get your transformed line. And then for the subtraction, it's the same concept. You can take your y-intercept and move it down 5 spaces. So that's what's happening here. So you can recognize the different transformations of a linear function. Example 9. Example 9 is the one that's blank, and this is what you would want to add to your notebook. So what we show here, you want to copy it to your notebook. So we're working with y equals -3, x plus 4 squared plus 5. Our parent function is y equals x squared, because when we take out all these transformations, that's what we're left with an exponent on the variable. So there's 3 different transformations happening here. We're going to make a quick sketch and a table for each transformation. And so for this one, we have -3 is in the A spot. We have 4 here, so that means that -4 is H. And then we have 5 for K. So these are my 3 transformations. The first thing I would do is make the parent function table and graph. So -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, and 2 squared equals 4. This is the graph that goes with it. You can see that we're looking at a coordinate 0, 0, and then we're imagining -1, 1 to be somewhere here, and 1, 1 to be somewhere here, and then 2, 4 to be about there. When we move on to the next table, the first transformation is -3. So for A, is going to multiply my A values by -3. So the x's are going to stay the same. So I'm copying those over exactly the same as what they were. And I'm changing each one of the y values. So 4 times -3 equals -12. 1 times -3 equals -3. 0 times -3 equals 0. 1 again, and 4 again. So now you can see in blue, we've noticed where 2, 4 is. So if 1, 2, 1, 2, 3, 4, we're sort of imagining a quick sketch of that being the coordinate 2, 4. Into the next table, what happens is that it goes from 2, 4 down to 2, -12. So the x stays the same. It's still 2 on the x-axis, but instead of going up to 4, now it goes down to -12. Okay, so that's what we're going to notice between the first transformation and the parent function. Now we're going to move on to the next transformation, and you can see here H is up next, and that means that the y's are going to stay the same and x's are going to change. So we're going to take each one of those y values here and copy them over exactly to this side. Whatever it says, that's what you transfer. So now you can see that the x's are going to change. -2, if I subtract 4, I get -6. -1 minus 4 gives me -5. 0 minus 4 gives me -4, right? And so from here, we can keep going. But I want to highlight the vertex on here. You can see for the yellow, it went from this point for what it was. And when I subtract 4, I'm going to be moving my vertex over 4 spaces. And every single other point is going to move left 4 spaces with it. So from wherever it was, it's going to move 4 spaces to the left. So you'd basically be plotting these coordinates, and this is the change that would happen to them. Okay, so now moving on to transformation 3. This is k. K changes the y values. So I'm going to copy the same x's because those are not changing. The y values are going to be adding 5. Negative 12 plus 5 gives me negative 7. Negative 3 plus 5 gives me 2. 0 plus 5 gives me 5. Negative 3 plus 5 gives me 2. And negative 12 plus 5 gives me negative 7. So each change to the y values, I'm adding 5. And you can notice what's happened to the vertex again. You can see how it was here, and I've moved it up 5 spaces. So it went from negative 4, 0 to negative 4, 5. And this is now my final answer. I've done all 3 transformations. You can see what's happening in each transformation. The first thing that happened was that the negative made the graph flip over. The 3 stretched the graph down more. Then the H moved the graph 4 spaces to the left, and then K moved it 5 spaces up. And then you have your final answer. Example 10, we've got a different parent function now. Now we see that we have these absolute value bars around my variable. So I know I'm working with an absolute value function, and then this is the equation for that parent function. So to identify that, we would say y equals the absolute value of x. That's my parent function equation. When I look at the different transformations that are happening, I kind of treat absolute value bars just like they're parentheses. So you can see that you have this negative in front of the bars, which is the same thing as having a negative in front of the parentheses. That tells me that's my A. And if there's just a negative there, then I know that that means it's negative 1. So I get A equals negative 1. Then I see inside of the absolute value bars, I have a minus 4 here. That's H because it's inside there with the X, not written outside of it to be the K. So it's H and it's opposite sign, so H equals 4. Now I can make my parent function table, and you can see what I'm doing in order to make it. I take my negative 2 and I plug it into my parent function. The absolute value bars, what they do is basically just take a negative away. They don't switch the sign, they only take the negative away. So if I put in a negative 2 in there, I get a positive 2 to equal y. But if I put in a positive 2, I still get a positive 2 for the y because it only takes away the negative. So you want to recognize the difference between a quadratic function with x squared versus an absolute value function with these bars. Okay, because the way that you graph the coordinates is going to be different. Instead of making that curved U shape with my coordinates, I'm making straight lines. That's what absolute value bars do. Okay, so when I plot these coordinates, negative 2 goes to 2, negative 1 goes to 1, and 0 goes to 0. 2 goes to 2, and 1 goes to 1. Okay, so I have the same sort of situation where it's paralleled on both sides, but it makes a straight line. So I'm going to pay special attention to this coordinate here with 2, 2. That's this coordinate right here. When I move into my transformation, my first transformation is that A equals negative 1. So that means X values stay the same and Y values change. I'm going to take each number and multiply it by -1. 2 times -1 is -2. 1 times -1 is -1. 0 times -1 is still 0. 1 times -1 is -1. And 2 times -1 is -2. So these are my changes. So I'm going to pay attention to what's happening from these coordinates. You can see how this coordinate went from 2, 2, and now it's moved down to -2. So 2 now gives me a -2 instead of a +1 like it did before. So I'm taking it and I'm transplanting it to there. I'm not moving it down, I'm basically transplanting it, would be a better way to describe it. So now we've done our first transformation, we're going to move on to our second one. We're looking at h equals 4, so that means y values stay the same. They don't change, I just copy over whatever they are. Now I'm changing my x values. I'm going to take each number here and multiply it by, I'm going to add 4 to them. So -2 plus 4 equals 2. -1 plus 4 equals 3. 0 plus 4 equals 4. 1 plus 4 is 5. And 2 plus 4 is 6. So each x value changed based off of the previous table. So we're going to look closely at the vertex of this function. You can see how it used to be here, and now I'm shifting it right 4 spaces because h is a +4, so I move right 4 spaces, and that's the coordinate 4, 0. Okay, example 11. We've got now a different parent function. So you can see we have this radical here. There's no number on that radical as like a little indicator of what root we're taking. So that tells me it's the square root. So my parent function is y equals the square root of x, because I'm going to take out those transformations to get my parent function. You can see under the radical is h, because we've said here h equals -4. It's the opposite. And then k equals -5 because it's the same. But inside the radical is h and outside the radical is k, the same way with the parentheses. Inside the parentheses, outside the parentheses. Okay, so now we have our transformations. We're going to make our table and a little sketch of the graph. You can see in our parent function table, -4 doesn't have an answer. We cannot take the square root of a negative number. But we've chosen, instead of the numbers we typically use up here with -2, -1, 0, 1, 2, now we're going to be using these different numbers. The reason why we're choosing these is because you get a whole number when you take the square root of them. Like I can do the square root of 4 and get 2. But if I tried to take the square root of 2, it would give me a nasty decimal. So we don't want to use these same numbers. We've just basically changed the 2's into 4's so that it's possible to take the square root, except for these 2 negatives. Whenever you're graphing a parent function for a square root, you wouldn't include negatives, but I want to show that those don't give answers. So we have to start at 0, 0, and then 1. If I take the square root of 1, I get 1. If I take the square root of 4, I get 2. So that's how I get my answers. So I have a coordinate here at 0, 0, then I can imagine 1, 1, and then I can imagine 4, 2 to make that graph. The first transformation is h, so that tells me my x's are going to change. I'm going to copy over these same numbers for the y values. So 0, 1, and 2 get transferred, and each x value is going to get subtracted by 4. -4 minus 4 is -8. -1 minus 4 is -5, and so on. So we're going to notice our vertex, it used to be here, but now we're going to go back 4 spaces to the left. That's transformation 1. Transformation 2 is k. We have the -5 on the outside. So we're going to copy exactly the same x values, get copied over. So -8, -5, -4, -3, and 0. And the y values are what's going to change. We're going to take the 0 and subtract 5, 1 minus 5, and 2 minus 5. So each point gets moved down 5 spaces. So this coordinate somewhere up here is now moved down to there. And you can see the vertex, it went from -4, 0 right here, and went down 5 spaces to now be there. So then you've got your final answer because we've done both of those transformations. All right, example 12, we're going to be looking at b for a minute. So this is what b does. It multiplies the x values. It does the opposite of whatever operation it says, and it's going to stretch or squish the graph horizontally. So we're doing a quick look at this just because we're not going to use it very much, but it is important to know something about it. So example 12, we're told to make a table and a graph for y equals 2 times x squared. So now we have this multiplication happening underneath the exponent. So that's how we know that it's b. And you can see parent function still y equals x squared. So same parent function table, except we're going to be using different numbers so that we can get a good idea of what b actually does, because the -2, -1, 0, 1, 2 is just too small. We don't really see what's happening. So we're choosing bigger numbers for x. We wanted to use 6, 4, 0, -4, and -6. Okay, so then the y values that go with those, 6 squared is 36, so y equals 36. 4 squared is 16, -4 squared is 16, and -6 squared is 36. Okay, because -6 times -6 equals a positive 36. Okay, so b tells me I'm going to change the x values. So my y values are going to get copied over and be exactly the same. And each x value, okay, is going to be edited to adjust to what the transformation tells me to do. So one of the things we need to notice, right, is that in the equation we see that x is being multiplied by 2, but the note here tells me that I have to do the opposite of the operation that I'm seeing in the equation. Just like how with h, it says minus, that means I add. It's the same thing for b. If it says times, that actually means I need to divide or multiply by that fraction. So if it says times 2, what I'm actually doing is 1/2. 1/2 is the same thing as dividing by 2. So if I multiply by 1/2 or I divide by 2, it does the same thing. For example, 6 divided by 2 equals 3. 6 times 1/2 also equals 3. It does the same thing. So that's why here we've got in our transformation, we're saying that b equals 1/2 because it says times 2, and the opposite of that is dividing by 2. So for each x value, that's what I'm going to do. So it says 6. 6 divided by 2 is 3. 4 divided by 2 is 2. 0 divided by 2 is still 0. -4 divided by 2 is -2. And -6 divided by 2 is -3. So each of these has changed by the factor b. You can see in the sketch of the graph here, and if you need to pause it and count or whatever it is, you can do that. But if you look closely, you can see the orange here is the parent function. So from the parent function, 0, 0, 4, 16, 6, 36. You can see how it's created the graph. And you can just kind of imagine that 1 would go to 1 and then 2 would go to 4. It's just a little difficult to get the graph drawn correctly, but you can see that it does fit right on the -2 side. So just imagine that this line actually does make it up to 4 on that side. But here's roughly what the parent function looks like. And then the pink is what is our transformation. So we have now, instead of 6 giving me 36, now 3 is actually what gives me 36. So I'm taking the point that used to be over the 6 and transplanting it to the 3. So now 3 gives me 36. And you can see 6 divided by 2 equals 3. So it goes from 6 to 3. All right, so that's just a quick look at what B does. We're going to look now at a different type of question, but you'll see these in some of the practice problems that you get. So we just want to talk about those of how they work. So example 13, we're given this function, f of x equals 2x plus 3. And so then they give us this description. They say that g of x represents f of x if it is reflected over the x-axis, stretched by a factor of 2, shifted to the right by 4, and then shifted up by 5. Okay, so that's a lot of things. So we're going to kind of take it step by step. So I've color-coded what each thing is talking about, and because we know what the transformations do when we see them in the equation, we can work kind of backwards and go from what they do to actually making the equation. So the first thing it tells us is that g of x represents f of x. So we know we're trying to make an equation for g of x based off of what f of x is. So we take f of x, we change it, and then that's what g of x is. So the first change we're told is that we're going to take f of x and reflect it over the x-axis. So that reflection over the x-axis is what tells us that we know that in front of the function, there's going to be a negative. Because when we take a y value from the parent function and we multiply it by negative, if a is negative, we know that that's going to make it go from above the x-axis to below the x-axis. So that's what it means to reflect it over. It goes from above it and flips over, and now it's below it. Okay, so reflected over the x-axis, you can see that it matches the color here in pink, that color in pink, so that negative there came from that description. The next description is saying that it's stretched by a factor of 2. So we can see that's telling me when it says stretched or squished, right, like the stretching, is A. That's what A does. In those notes we have at the top of the first page. So that tells me if it's stretched by a factor of 2, that tells me A is 2. So I change that. So I have -2 now. So these two pieces right here give me an indication of what A is. If I wanted A to be a fraction, it would say stretched by a factor of 1/2, and then that's what the A would be. So I have here the next one, shifted to the right by 4. All right, left, right. We know left and right is H, and we know that it's opposite of the sign we say. So if it's right by 4, then H here in green has to say -4, because it's the opposite. Right goes in the positive direction, but actually we want it to say minus. Okay, the next one we see is shifted up by 5. That's K. K is up and down, so we add 5. So you can see these are the transformations that I'm pointing out to you, but I just want to make sure you're aware. Like, so what we're doing here is we're writing the function for g of x. So g of x equals this in terms of f of x. So you'll see this. Write the function for g of x in terms of f of x. And this is how you do that. So you can see that we have g of x equals, and then we set up this f of x, just like it's written here. So this is how we write it in terms of f of x. We have f of x, and then from that, we put the -2 in front of it, because that's where a goes in the equation. Then we put h inside of those parentheses with the x, because that's where it goes in the equation. And then the k goes on the outside, because that's where it is in the original equation. So we're treating this f of x like it's an equation. So to write g of x in terms of f of x, this is how you write it. All right, so step 2 is to do a different thing. Step 2 is to actually figure out what is the equation g of x actually. So to do that, instead of writing it with the f of x here, we need to write what f of x equals. So we have 2x plus 3 here. We can see that if I had 2x plus 3, okay, here with the x, I'm going to put parentheses to show where we're doing things at. So you can see how, because I have this whole equation here, the 2x plus 3, around it I'm putting parentheses because this -2 for the a is multiplying to everything of f of x. So that's why I get parentheses around it in orange here, to show that -2 is being multiplied. So you can see how this is where it lines up in the equation. These are the pieces where they came from. Okay, so all around it is a, because a is being multiplied to the whole thing. You can also see on the outside is the plus 5, because plus 5 is being added to this whole thing. So that's outside. Okay, inside of the equation, where the x is where we put the h with the x in the parentheses. Okay, so that's where all the pieces go when you're trying to figure out what g of x actually is. From here, now you just start to simplify, okay? So 2 gets distributed to the x and to the -4. So you can see that that's what this turns into here. And then 2 times -4 is what we get from the 8 here, -8. And then that +3 just sort of drops down next to it. So we did the distribution, that's this piece, becomes this piece. Okay, then we add 3. -8 plus 5 equals -5. So now we've combined these like terms. The x can't be combined with these because they don't have x's. So the 2x just sits in front, and then these combine because they're like terms. So now we have 2x minus 5. So the inside of these parentheses has been turned into that. Now we'll start dealing with the outside. So we have to do multiplication before we do addition. So we'll distribute the -2. So -2 times 2 is -4x. -2 times -5, the double negative, gives me a +10. So this here now is how I got this. Okay? So then this 5 on the outside just drops down, and then you can combine like terms again. So because we've completed the parentheses that we needed for the multiplication. So distribute -4x plus 10, and then the plus 5. 10 plus 5 is 15. So that's how we get this final answer, -4x plus 15. So that's example 13. That's one of those that's the blank in the book, in the folder. So you want to make sure you add example 13 into your notes. So copy that into your notes. Example 14 is just another example to reference for the way that this whole process works, just so you can see what happens if you don't have a number mentioned for A, just so you can see why the negative still works. So we're going to use the same f of x, but this time we're going to make a different function. We're not making g of x anymore, we're going to make h of x. And h of x represents f of x if it is reflected over the x-axis, shifted to the left by 4, and shifted down by 5. Okay? So these are some opposites of what we saw before. All right, so first, to write h of x in terms of f of x, we're going to have h of x equal, and then we're going to set up that f of x there, and we're going to plug in the things that it talks about. So reflecting over the x-axis, there's that negative there. It's like implied that it's also a -1. You can write it as just a negative, or you can write it as -1. It's up to you. Then you see that shifted to the left by 4. Left goes in the negative direction, but h is opposite, so we write +4. Then shifted down by 5, so now we've got subtracting 5 here. Okay, so that is h of x in terms of f of x. That's potentially an answer to a question you'll probably see. Step 2, though, is a different kind of question where you're now supposed to say what h of x actually is. And the way that we do that is we replace that function notation with 2x plus 3, because that's what f of x is. So it's the same process as we did before, where we have, you can see the 2 and then the x and then plus 3. And it's the same concept, where you can see 2 and then x and then plus 3. Okay, so then outside of the whole thing, we're multiplying it by -1. Then inside the parentheses with the x, we're adding 4. And then outside of the whole thing, we're subtracting 5. So now we'll start to simplify. Distribute the 2. 2 times x is 2x. 2 times 4 is 8. Then combine like terms. 8 plus 3 is 11. Then distribute that negative. Negative 2x, negative 11. So negative 2x minus 11. Drop down that negative 5. Combine like terms. Negative 11 minus 5 equals negative 16. So now my final answer, I see negative 2x minus 16. So that's my answer for that question. That's all of the notes for this section. We'll see you in the next one.